Okay, thank you very much for attending this talk. And today we will talk about the area access network for 6G. We will talk about from UAV to HAP to satellite communication. And my name is Zhu Han in the University of Houston. And this one is based on the 3-hour ICC tutorial, and which we posted on this website. And also we greatly thank Professor Lin Yangzong, Bian Kai Gui, Sheng Min, and also Dr. Hongliang Zhang, Dr. Boya Li, Dr. Di Zhou, and also Ruo Qi Zheng, and Zhang Shuhang, and Jia Ziye. Okay. And here, let's talk about the objective. First, let's talk about what is we try to introduce the area access network. And also, we try to tell what is the infrastructure and what is the user, and how to integrate the space and the terrestrial network. And then we try to learn some kind of basic problem, and then how to optimize them. And we talk about optimization and game theory. And finally, we show you many examples on how to formulate, how to integrate AAN, and how to make the problem as an optimization problem, as a kind of other type of problem. So how could you do the problem formulation? So this is a third thing. Okay, we have a chat. Okay, and here the table of content. We talk about 6G and AN first. Then we talk about the mathematical tool. I will omit the optimization theory today and talk briefly about the game theory. And then we talk about this cellular internet of UAV and its applications. And then we talk about HAP, which is basically these balloons. And then finally, we talk about the satellite network. So this is the thing. I will stop in the middle, and then let's see. Okay, let's see. Okay. And finally, we try to talk about integration. So for mobile communication network at the beginning, it's a kind of very old. And in 1980s, we have big to the voice, and now we have everything to the data and so on. So in 1G and 5G, which is the first wave, we try to make the people connected by voice. And in 3G and 4G, basically mobile multimedia transmission. There's an iPhone, and then everything becomes a smartphone. And then this is caused a big kind of a surge in the second wave for the communication. In 5G and 6G, there will be a new business value, and there are some kind of human-centric value and many, many things. And so this one will give you many new applications. For that reason, nowadays the competition for this 5G and 6G is very, very severe. So for 5G, when you talk about 5G, you will talk about three problems. So this triangle is very important. But on the top, you have the capacity enhancement, EMBB. So the capacity enhancement basically, especially at the edge, at the edge of the cell. So the solution is an EMBB, all this kind of a small kind of mobile station. On the left is a massive connectivity, basically means Internet of Things. So there will be billions or trillions of devices on the ground. And how can you make them connected? So in this case, MMTC is a solution. On the right-hand side is ultra high reliable and low latency. And this one, basically URLLC, basically is for this unmanned driving or gaming something. So you need to have very quick response so that, the car will not hit the other. So when you talk about the 5G, this is a three major problem, and it's a triangle. The problem is well formulated, and but on the other hand, the technique to achieve these three goals is very diverse. They can have all kinds of things. Unlike 1G, 2G, 3G, 4G, they have their unique technique, like this, this TDMA or OFDMA, something like that. In 5G, there's no unique kind of technique, but instead there are a lot of different techniques to achieve these three things. And then for 5G, there will be many applications. VR and AR, and the industrial IoT, automatic driving, and then now we have COVID-19. We will have the VR for education, and also the UAV is a very hot topic, which I will talk later, and then smart coordination. And when we look further to the to this 6G, okay, in the future, and then okay, and they will have a many kind of intelligence information. So basically, they will have a higher data rate, and the coverage 5G. The problem for 5G is that the base station is too small. Okay, sorry, the base station coverage is too small, just a small area with very high data rate. However, you need to have a very kind of in the middle of nowhere, okay, you also need some kind of coverage. In this case, what you can do, and lower access latency and smarter device. And also, okay, there are many other things, new multimedia, new interference, new architecture, like today what we are talking about, area network, and new fusion, about the communication, computing, control, and caching, and so on. So I have another talk on my website about this issue. Okay, then just like a 6G, okay, just like 5G, okay, there will be a many different techniques to implement the 6G. And moreover, what is the 6G? Nobody can say that. Not like 5G. 5G is already well defined, and people try to implement it. 6G, people have no idea about what it is. So in this talk, we talk about one possibility, very plausible probability. As a matter of fact, it's already begin the standardization, which is an area access network. So the basic idea is that, okay, you are connected not only by the base station, but also by the other possibility. For example, the UAV, the balloon, the HAP, high altitude platform, the satellite, or you're on the sea, you are connected by this ship. So all these things are integrated together through this gateway and so on, something like that, so that okay. And also there will be AI to control this one. So this is a basic overview of this area access network. And the component of the area access network consists of the satellite, UAV, and the HAP, which I will discuss later. And also we have the terminal. You have this kind of handheld devices or access point. And then, okay, later I will tell what's different, okay. And also we have the gateway. Sometimes you need a kind of a hub to get this kind of, to connect to the core network. So basically, okay, when you consider, you should consider them all. Moreover, pay attention to the terrestrial terminal and the gateway, which is very different. I saw a lot of paper with UAV, HAP, and satellite only, but sometimes you need to consider this, the terrestrial terminal and the gateway. I will tell you why in a few slides. So the role of AAN in 6G is extend the coverage, and then basically there are many unserved areas like the Sahara place, okay? And so basically you need to have a wide enough coverage and improve user experience to reinforce 6G service reliability by providing service continuously. So basically, if you have the M2M IoT devices, okay, and placed in the Amazon jungle, for example, and then how can you collect the data? And the multicast and the broadcast, obviously the satellite have the huge advantage on the broadcast issue. So this is the role of AAN for 6G. So for UAV, typically is located on the low altitude, and then because it's sometimes battery or sometimes this kind of oil engine, so it can last hours, and then minutes to hours, and the coverage is very small, and sometimes most of them use a battery. The controller can be on the ground or the other places, and the application is sensing, surveillance, and communication. For HAP, basically, okay, it's a, oh, this is a, I think here is wrong. Actually, the photo is wrong, okay. The HAP is a basic balloon, okay. It's can be hours to months, and then it's about 17 to 20 kilometers up. So basically, okay, it is a kind of very, very robust to do that. And then, okay, 1 second. Okay. Okay. And then they use a solar panel or battery, so they can survive there. And then they can control by the ground or the satellite, and then can do the real-time monitor and the emergency recovery, rocket launch platform, etc. And the satellite is above 100 miles, and it can be there for years, and it's large and periodic. They use the solar, and then they have to control by the ground, and for the communication, relay, weather, and so on. So also for satellite, they have a 3 type. The first type is LEO, basically lower orbit, all this kind of harbor, all this kind of international station, or this all this kind of this GPS, and also this Starlink, Elon Musk located right here. And the good thing is very close, and but the bad thing, the visible time, but the bad thing is moving away. So your visible time is only 20 minutes. So you need a lot of satellite to cover it. And for MEO, typically around this region, and then, okay, typically, okay, is synchronized to the polar. So in other words, for the MEO satellite, it will go north and then go south and go north and to go south. So just on top of you, will not go to the east and the west. And in this case, okay, for example, for satellite XM, they have a 3 MEO satellite. And so some to cover this kind of North American and South America. And then they go north and south, north and south. So in this case, okay, they 3 satellites, they can already cover all the service. And finally, it's a geo satellite, which is really far away. And then it's a fixed here, your direct TV, you put the antenna and then try to, your kind of satellite TV, okay. You fix the location and then you get all this information. So they have the pro and the con. Pay attention to the delay, and also whether or not they are moving. So basically, okay, they are kind of have the different property. And then for the ground station, you will have this Earth gateway, which is a control and signal processing. And also the major information is collected here to the core internet below. And then the diameter is 5 to 13 meters. And also, okay, they only have very limited station because it's very expensive. Moreover, okay, downlink is fine. For uplink, the power is so strong. For example, for uplink to the geosatellite and then come back, the signal kind of will have 200 dB kind of path loss, which is a 10 to the power of 20. So the signal will drop significantly. So in this case, the uplink power is very strong. And then this power, okay, around here, no human can live there. And when I was have senior design, I saw the bird flying on top of it and then get cooked and then falling down. Okay, yeah, it's just a open microwave. Okay, very, very powerful. And on the other hand, okay, there are some kind of a very small aperture terminal. For example, it's a small satellite connected to it, and then they can connect to the small satellite and then try to connect it everywhere. For example, okay, after I got my degree and I drive to this American Wild West, in the middle of nowhere, okay, I go to an Indian reserve and then try to buy something. And I asked, I don't have cash, okay, do you receive credit card? He said, no problem. They have satellites. They can charge me anytime, anywhere, okay. So this is the case. And moreover, this kind of, frequency, the frequency is also limited. For example, typically for satellite TV, they have a C-band, and they have a KU band and a KA band. So basically, okay, this is a basic story. And then you only have the limited kind of bandwidth for transmission. For C-band is this kind of big antenna. For Ku band, it's basically your direct satellite TV. And for Ka band, it's your satellite phone. So this is the case. Because for the other frequency, either is used by the other kind of, other this kind of application. For example, X-band is used by radar, this SAD, okay. Anyway, it's this kind of X-band. And or some of the bandwidth have the absorption, have this kind of, atmosphere absorption. So it cannot go out with, to the space easily. Okay, and then, okay, then we have this kind of UAV part. Let's talk about lowercase. So we can have UAV at the base station and to do the data offloading, emergency communication, or have the relay to improve the coverage and the QoS. Or UAV can have a user to do the survey or to do the other job. And later we will show you the example. And then there are many kind of UAV projects, like this kind of Nokia, Facebook, and etc. And for HAP, high altitude platform, is basically balloon, which is located in 10 to 20 kilometers above. There's no weather condition there. And so in this case, they can have serve as a flying infrastructure, which can cover many places. And also because the link to there is great, there's no kind of scattering around. So the hub can be working as a backhaul to this kind of overall network. And the existing hub project is Airbus one, Google balloon, and all these things. You see that this is a kind of just a balloon. And also in Taiwan, I also saw a balloon in the university. And then for satellite, can be used like a kind of backhaul or coordination, and try to connect it together. And satellite working as a remote base station for broadcast and multicast to transmit. Okay. And also, okay, currently we have the ultra dense topology evolution. We have the seamless coverage versus a low propagation delay kind of thing. If you want to have a low propagation delay, unfortunately, your base station has to be small. And if you want to have, however, you don't have that, enough money to put all these 5G stations everywhere. So you will have this coverage problem. However, if you use a satellite, which is great, okay, coverage is perfect. But think about what's the round trip delay from here to the satellite? At least 100 miles away. So in this case, okay, you will have trade-off. And for each satellite, long propagation distance lead to degree of spatial diversity due to the higher correlated channel. And the ultra-dense LEO satellite constellation and the coverage extension via hundreds of satellites. So that's the reason, okay, this Elon Musk want to send, dozens of thousands of satellites to the sky. Because if they put the ultra-dense LEO satellite constellation, the coverage extension via hundreds of satellites, and then they can have many spatial diversity by obtain the satellite coordination. And for satellite, because at a specific time, you will know exactly the location. So in this case, the problem is deterministic. So in this case, you can find the optimal kind of satellite to help you for that. And also the backhaul capacity is improved because there are so many satellites around. And this is SpaceX. And I think today they send another link up. So basically, okay, they will they have sent a lot. And also Telesat, basically this is a Canada company. And also for A2G channel, you will have this kind of below 6G or above 6G. And then they have a different property. So for below 6G, you will have no ring attenuation, but for above 6G, you will have, okay. And below 6G, you will have a frequency selective channel. So you have to use OFDM, something like that to overcome. And for above 6G, it's flat. And then, okay, they all have the line of sight because for satellite, you will see this kind of, I mean, you will go outdoor, okay. And then transmission noise level, and for satellite HAP is this level, and UAV is this level. And antenna ratio is a small factor ratio pattern. Above CG is a large roll-off factor. And the channel model is typically rising channel. And because you have a line of sight and scattering around you, okay. And it's very interesting, okay. For downlink, it's rising channel. For uplink, might not, okay, because around satellite, there's no scattering. So for uplink, maybe this kind of large propagation is sufficient enough. Long distance, I mean, large scale propagation model is sufficient enough. And also, okay, below 6G, you can use this kind of a cell phone. So for example, for the cell phone one, you can directly connect to the constellation. Above 6G, you cannot use a cell phone typically, okay? You have to use this kind of station. For example, for SpaceX, they say that, okay, typical cell phone cannot connect to the Starlink. Instead, you will have a small base station, and then small base station will change to Wi-Fi. So this small base station will communicate above 6G. So this is a difference, okay? So when you select the frequency and pay attention to this kind of difference, okay? And also the A2G model below 6G for UAV, they have a standard. So basically this is a kind of a height, and also this path loss with a different parameter and angle. So for UAV channel, okay, the standard the standard is already there. So do not use this kind of I mean, arbitrary use it. So in the old paper, before the standard, there are indeed some different type of model, but nowadays, okay, it's more kind of consistent. So basically, try to use this use this kind of standard model, okay. And also, okay, the channel model for UAV, okay, if the UAV is flying, this is a UAV height, UAV height, and then, okay, this is a horizontal distance between the user and the user. So you will see that, okay, the optimal height will be different due to the triangulation, okay, and also this type of thing. So in other words, okay, from this figure, what I want to say is that, okay, this is a 3D. So when you consider this resource allocation, and sometimes it's a counterintuitive, and sometimes it's not, I mean, counterintuitive. If your UAV is too high, well, the coverage is better, but I mean, the distance is long. So the 3D kind of optimization and become, the optimization over the 3D space become a very interesting. So typically they will give you some counterintuitive result. And typically for channel, you will have this line of sight. It's basically typically they can have the log normal. Non-line of sight, they use really combined together is rising channel, and then you have the ring attenuation. So for ring attenuation, this is show you the example for different ring or something like that, and it's indeed. And my senior design is about ring attenuation. We design a board and then try to measure this kind of ring attenuation, and then use this terrestrial internet to send back to the transmitter. If there's a higher ring attenuation, ask the transmitter to increase the power. So we have this closed loop power control. And then, okay, after I finished my project, I'm supposed to graduate in May, but in Beijing, in summer we don't have rain. So finally I graduate in August, waiting for the rain. Okay, so this is just a kind of story. And so satellite, the ring attenuation will indeed have dozens of dB kind of difference. And also there's a difference is that, okay, for angle spread, okay, for satellite, okay, you only have one path, one direction, okay. Well, for this kind of angle spread, for this kind of terrestrial, you will have a difference. And for air-to-air channel, typically, okay, for satellite to HAP or HAP to HAP, you will have a free space model. Why? Because around the satellite and around HAP, there's no scattering. Unlike when you use it on the ground, I mean, around me, all this scattering will cause a Rayleigh distribution. Line of sight Rayleigh distribution. All this scatter. But for satellite to the HAP and HAP to HAP, it's just a distance, two distance. Around them, nothing there. And then, so you basically use a large distance model. And also, okay, for UAV, they have this propulsion energy. And you have velocity and acceleration. And for fixed wing propulsion, so overall, these kind of energies look like this. It's not only depending on the speed, but also acceleration, and also to the speed power 3, because we have this kind of air resistance. Air resistance is a kind of quadratic to this kind of speed. So that's the reason. But this is for fixed wing. For rotor one, okay, you can check the literature to find one. So sometimes you do the energy kind of conserved resource allocation, and for your battery, proportional battery, and try to check the literature to make sure that okay, your model makes sense. Do not use those too simple, too naive one. Okay. And for satellite, okay, they have this kind of the major difference for the satellite and UAV is that okay, for UAV you can control the location, fly different places, but satellite is fixed. At a certain time, I know that which satellite located at where, and also this coordinates of each satellite will satisfy this equation, and also okay, the orbit, the time slot for each satellite, a time slot can be kind of accurately calculated. So this is a case. And the AAN and the terrestrial network, when they compare, for space, they have the GEO, MEO, LEO. For air, they have this kind of HAP and UAV. For terrestrial, they have the cell phone, ad hoc, and wireless LAN. And then the delay. This is a delay. Pay attention. And the coverage. Okay. And the advantage is the coverage versus this speed. So basically, this is in the middle. And the disadvantage is also the vice versa. This kind of propagation delay, ring attenuation, and for air one, basically okay, this time that you can stay there, and also because the air fluctuation. And for terrestrial, it's expensive, and so basically okay. In 6G for AAN, how can you integrate space, air, and terrestrial together? It's indeed a very hot topic. And the research challenge is for optimization. You can have scheduling, treasury design, co-channel interference, and distributed learning. And for the protocol design, you have the self-organized network, routing, handover, spectrum leasing issue. For network deployment analysis, you have constellation design, capacity and outreach analysis, etc. Okay, so basically, okay, this is a kind of very basic, and for this 6G and AAN, and here I just mentioned several things, and the key point here is that okay, when you excuse me, and when you formulate something, okay, try to remember this physical meaning, okay, and try to kind of think about this one makes sense or not. And for example, okay, recently my students try to do the energy conservation, and then try to minimize the UAV power plus this base station power. You know, what is UAV power? Powered by battery. Base station is very energy consumption, right? So basically, you add them two together, doesn't make too much sense. Okay, so and also for delay, okay, for example, okay, and you want to have this ultra low reliable URLC, then you talk about geosatellite. Then doesn't make sense, right? Because round trip delay of the light, how long it is. So pay attention to physics, okay, and also remember that the major component there, beyond this kind of a HAP, satellite and UAV ground, you also have the gateway and also some other things. Anyway, so the second part we will talk is this kind of mathematical tool. And I will omit the optimization in this talk, and I will talk about optimization next one. And then, okay, you can go to my website. We have 40 hours of optimization and the game theory slide there. And here I just use maybe 30 minutes to finish it. Less than 30, maybe 15 minutes to finish it. Okay, for game theory, there are many different types. And then today, okay, you can go to our book. Those are 3 books related to game theory, both out by Cambridge University Press. And today we only talk about matching theory and mean field game. And for game theory, it's a mathematical tool to for network economy and for economy. And the game theory have adopted many kind of things in various network. And the key story is that you have a player which selects a strategy such that they can gain their payoff. But then the major difference between the game theory and control is that, okay, for control, you are doing your action against the nature, such as the noise and or channel unstable or something like that. And for game theory, your payoff function is not only your kind of strategy, but also the other strategy. In other words, you are trying to kind of doing things against nature as well as the other. Okay, and for example, okay, I hope that okay after this one and after this talk, you guys can write beautiful papers. But when you submit it out, okay, all your peers will review each other, and then it will be a game. I'm just joking. Okay. And here is some kind of very basic one. You have the non-cooperative game, basically non-cooperative static game. Basically, non-cooperative static means play once, and the most famous one is the prison dilemma. And Harry and Dave got caught by the police. If they play non-guilty, they go to the jail by 2 years. If they blame each other, if one blaming the other, the blaming guy will get less penalty, and the blamed guy go to the jail more, and vice versa. If 2 blame with each other more, and then okay, they will go to jail. The police know everything, they will go to jail for 3 years. So this is a prison dilemma. Even though they cooperate, they can have less penalty, but because they are greedy, they want to have the one, then okay, finally it turns out they both have a worse penalty. And then to overcome this problem, you can play the game multiple times. And then you can give the threat to the other. If you screw me up now, I will screw you up tomorrow. Okay, tit for tat. So in this case, okay, people will become more cooperative. For example, during the Second World War, there's a theory called mutual assurance destruction, and which win the Nobel Prize. And then, okay, they basically say that if the Soviet Union and the United States will not have a hot war, because anybody starts the hot war will get retaliated, and the short-term benefit will be eliminated by the future punishment. So this is a repeated game. And for dynamic game, there's an ODE optimization. They're using HAP equation, and this is basically, if you don't talk about the game, about the kind of dynamic control, this is basically SpaceX. Okay, this is a rocket going up and then coming down. So suppose you have this game, which play over the different time. You have ODE there, and then the influence is not affected by one individual, but by multiple players. Then you will have the dynamic game. And if your state is unknown, you will have a static game. And finally, you have this on this page, you have the cooperative game. So basically, you have if the people can cooperate. For example, I have collaboration with KHU and Taiwan a lot, and then okay, this is a cooperative game. I can put my resources on the table. You put your resources on the table. Then let's cooperate and then have the mutual benefit. 1 + 1 greater than 2. And then after that, we decide how to divide the extra. So this is basically a cooperative game. And there are two types, Nash bargaining solution and coalition. So basically you have this player N and strategy S, and you have payoff. And then you have the complete information and incomplete information. Complete information is like chess. For chess, every information is on the board, so everybody knows for that. And then you can have the incomplete information. For the incomplete information, for example, the two companies want to compete with each other. They will know they don't know each other's kind of strategy. So this is a kind of incomplete information. And for Nash equilibrium, so as I mentioned, your utility function, UI, is not only depending on your strategy, SI, but also on the other strategy, S minus I. S minus I means other user. And if you happen to in this kind of Nash equilibrium, S star, and if you move from the SI star Nash equilibrium to any other kind of strategy, your utility will drop. In this case, we will not leave the Nash equilibrium. So in other words, no user can change its payoff by unilaterally changing strategy. Changing the strategy while S minus is fixed. So in this case, it's Nash equilibrium. And then typically for Nash equilibrium, it will have poor performance as we shown in the present dilemma. So when we have this kind of centralized solution, that means everything, there's a God know everything. So in this case, you will have centralized, constraint optimization, you will have an optimization solution. But distributed solution, you will have another solution. And then the ratio between the distributed solution over the centralized solution is called the price of anarchy. So basically means that, okay, the distributed solution, due to the greediness, the performance will be poor. So basically, okay, the whole game theory is regarding how could we improve the decentralized solution to close the centralized solution. However, centralized solution typically not working because of the too much signaling. And in practice, centralized theorem is just a performance bar. Okay. And here, let's come back to this present dilemma again. And then for any game, it's rational. The assumption is rational. So what is rational? Rational means the maximized utility is my only goal. I don't care about the other. So here is the format, and Henry and Leif, they can select the two actions, whether or not to quiet or think, to betray. Okay, and then this one. So if they spend quiet, they will have the payoff of fun one, which is and if one of them blame the other, the one blaming think one will have this protection, witness protection. Okay, you only have the set free, and then the other go to year 4, and vice versa. But if both blame each other, the police know everything, so they will go to the jail for more. So this is a Nash equilibrium, and this is periodic optimal or centralized solution. What is the periodic optimal? Periodic optimal means that, okay, you cannot improve your performance without hurting the other performance. So this is called periodic optimal. And then there are different algorithms, like this kind of, finding the Nash equilibrium sometimes is NP-hard, and then you can use a fiction play, utility algorithm, batch response, and so on. There are some good reference, and as long as your utility function fits certain criteria, and they already show that, okay, it converges to the optimal solution, it converges to the Nash equilibrium. So there are so many kind of, about I have 40 hours of this kind of different game, and we are still starting a new game. So in this talk, we only talk about 2. Matching theory, the first one is matching theory. The matching theory is that, okay, we have a man and a woman, and we found a date, finally we have the kind of marriage. So, and then we want to find the matching to minimize the unstable marriage. And then how to design the algorithm to find this one. So you can consider this is a user, this is the resources, how can you match them together? Okay. and we have a book for this matching theory. And in economy, matching theory is a mathematical framework attempt to describe the formation of mutual benefit relationship over time. So they have an agent, I mean, this kind of man and a woman, and then we have the preference list. So basically, man have the preference list, I mean, Lin Zhiying, and this, what is the Korea pop star? Okay, and so on, something like that. So on your list. And then we have blocking pair. So what is a blocking pair? So the blocking pair is that, okay, if a man prefer a woman, and then his wife, and this woman also prefers this man and his husband, and then these two, I mean, will be divorced and then marry together. So this is an unstable marriage. So we want to find this kind of matching to prevent such kind of unstable marriage. And then this is the case, and the algorithm Gale-Shapley give you a very simple solution. For matching, the complexity is n to the power 4 for finding the optimal solution. Well, for Gale-Shapley, it has the complexity of On, and sometimes it's even smaller because the preference list sometimes is very short. Okay, I only have very short preference list, and after marriage only one. Okay, and then okay, for this kind of I mean, I don't have this kind of 3.5 billion, right? 3.5 billion preference list. I don't need for that. Okay, I only need to have very short preference list, and in this case, the complexity is much smaller. Okay. But what is the Gale and Shapley algorithm? And Shapley won the Nobel Prize 2014 due to this algorithm. I see, okay. And then we have an item, he has a preference list, like the guitar, he liked guitar first, and then Heike, Irena, and Fran. And obviously he dated his top of the list, guitar. And Bob, this is a preference list, he dated Irena. And the cars also like guitar. So try to PK with Adam. And Gita think cars is more tall and handsome and rich, so Dan Adam. And then Dan have to find the second on the preference list. And David also like Irena and PK Bob and so on. So very quick, it will find a very stable marriage. So how quick it is? You know that each year I will recruit new PhD student in September. In December, it's already converged. Okay, unbelievable. Okay. Anyway, so and for matching, this is a very simple example. Okay, and then we have a much more complicated case. We have the one-to-one matching, for example, a marriage one, stable marriage one, unstable roommate. In American, okay, the roommate is have two roommates, and the many-to-one, like the house allocation, student admission, and money-to-money. And we will talk about this one later. So this is the first type of classification. Second type of classification is that, okay, whether or not with an external effect. So in other words, if somebody is already married, whether or not I will change my preference list. Okay, so basically this is a matching without the external effect or matching with external effect. The other action, whether or not will affect my preference list or not. And let's give the example, house allocation. So basically a set of application for a set of house. And this case, okay, the preference list, the application have the preference list of the house, but the house have no preference for this kind of application, but the house have the capacity. So basically, okay, you can find this solution for the Pareto optimal, popular, and the profile-based optimality. And the house allocation variation for review assignment. For any infocom paper, okay, your paper will be assigned to the reviewer by machine. Calculated by programmed by University of Toronto, Dr. Baochun Li. And you have the preference to, to the paper due to your expertise, but the paper have no preference to you. And each paper need to have this kind of a required minimum number of reviewer to do that. Okay, so basically, okay, this is a paper review problem. And oh, this is a kind of a joke. Okay, so reviewer 3, okay, it's always a kind of interesting. And reviewer assignment, then the consideration, you have a conflict of interest, coverage, load balance, and all those constraints. And then typically they use a Lamington optimal matching. So this is the algorithm they use. And for wireless oriented matching, you will have the user resources try to match it with the resources or agent. To the quality of service is typically the preference list. If I match with these resources, what is my quality of service? So that I can rank the preference list. And then we have the system objective, and then we have different solution. And for game theory, okay, we don't need to exchange the information, and also is stable and near optimal, and also okay, and also there's no necessary utility to function to define. You only need to define the preference list. So basically, this is a good thing. And so example, if there's a kind of matching, we have different server, you have the small base station, you have base station, then you try to caching the information to there. And 4 years ago, okay, my Taiwan PhD student who just graduated, he came from Taiwan, and his first paper is started a Twitter of a kind of a 2016 presidential election, and then okay, for the election, okay, and they will see the preference list for the different kind of CNN or Fox News. So around the campus, they will put this caching of CNN or MSNBC, those are left wing. For the place like this redneck, they will put the Fox News there. So basically, this is a matching. This is a matching. By using the machine learning and the matching, they can do the caching. And then the second story we are talk is about mean field game. The mean field game studied the existence of Nash equilibrium involving a large number of asymptotic and negligible users. So in the old time, when this kind of number is big, I mean, the optimization is very difficult to implement. But now, okay, what they do is that, okay, they use the mean field to quantify it. And after that, okay, the mathematics become much more simple. So the mean field, they are indistinguishable, very small, and rational. So basically, they want to improve their utility function. They are heterogeneous. For different time, they have at the same time they may have the different state. You can consider this one as a school of fishes, a lot of fishes. Okay. And then mean field game reduce the standard control problem to an equilibrium, and then can solve it very easy. So in classic game theory, for example, if you want to do a control, this shark try to control those small fishes, thousands small fishes, and then you have to do individual control, which will be very difficult. On the other hand, by using the mean field, you can consider this kind of school of fish as this kind of mean field, and then you do the control, and then you can consider them together as a mean field, and then in this case you only consider the shark against this school of fish, so just a one iteration, two user case, look like two user case, and then the optimization become much more simplified. So this slide is very interesting. So for traditional optimization, you change a parameter so that, okay, the objective function is changed, maybe with certain constraint. For optimal control, there's an ODE constraint below it. And this ODE for this kind of space X is just Newton law. It's a differentiation of the speed equal to acceleration, right? And then for game, compared with the optimal problem, your utility function is not only your control mu, but also the others, mu minus 1. So this is the game theory. And for differential game, okay, you will have this ODE here. And then for differential game, if your I is very large, there's no way you can solve it. So you consider yourself as mu, the other as an M, mean field. And then by doing this one, it becomes two user case. Okay, so this is the key idea. And the daily kind of example is that, okay, every day you drive out and then you against the traffic. You are not against the individual car. Okay, you are not racing against the other car. The traffic can be considered as the mean field, and you yourself, against them. So basically, this is the case. And then, okay, this is a school of fish, but this is not a shark. So in this case, okay, when the shark to attack this school of fish, they use the Hamilton-Jacobian-Bellman equation, like this one, to find their optimal control. But this school of fish will use the IPK equation to react this shark's attack, and so that it will change its kind of strategy. And then these two will iterate together until convergence. So this is the basic of the mean field game. Okay, so in other words, okay, you are not consider the mean, just mean of the school fish as a thing. That is not kind of active. As a matter of fact, you consider them together as active things. So there's still an ODE for this school of fish there. On the other hand, this school of fish is also not a kind of shark alone. And they instead of two HAP together, there will be HAP and IPK iterative. So that's a difference. Okay. And then for this kind of UAV, we have done a lot of work. And suppose we have a little money balloon. When they go up, the coverage becomes larger, QoS become lower. When they go down, the coverage becomes smaller, but QoS become better. So how can you control the height? You use the mean field game to control for that. And for UAV, they fly to the Internet of Things to do the charging. This is a kind of a many kind of ODE here, because every time the energy depleting follow some kind of ODE, and the UAV select where to charge, and then to collect the data. And then this is a hub with a NOMA, and then, okay, the mean field gate with a dominator, because there's a kind of a dominator at top, and the non-interference dominator. And in this case, okay, how can you do that? This looks like the shark tries to attack a group of fish. Inside the group of fish, there's a turtle. Okay, so this is the basic story. And finally, we have the multi-UAV emergency communication, and the UAV go to different places, try to find this kind of task. And also the multi-UAV with machine learning, and how can they kind of together with the mean field game, and how could they distributed learn where should go. Anyway, so this is some work. Okay, so what time is it? Okay, it's just 1 hour. And let's have a 15 minutes break, and let's come back at 10:10 in Taiwan, and 11:10 in South Korea. And then let's have a short break. And after that, we will talk about UAV, HAP, satellite, and integrate together about the example. So basically, okay, we will talk about several examples to show you that, okay, how could we formulate the problem. So hope to see you in 15 minutes.
Okay, thank you.
Thank you.
Yeah.
Hello, can you hear me? Okay, sure. Yeah, let's start. Okay, and yeah, so let's first talk about this. Let's first talk about. Give me 1 second. Let me check. Okay. Yeah, it's okay. Yeah, let's first talk about this UAV story, and we will talk about UAV as an infrastructure or UAV as a user. So before that, let me show you my UAV. This is a demo in Rice University. Rice is also in Houston. So, I mean, the university have the competition. Okay. Anyway, I'm just joking. And let's talk about this kind of UAV with infrastructure. Hold on a second, there's a little bit problem. Okay. And infrastructure at a base station, it have a low operation cost and it can fly everywhere. For example, there's a kind of natural disaster, all the base station destroyed, and then the UAV can fly there to get this one. And they can, as a relay, for example, in the west of Texas, and nobody there. So the UAV can be relayed to extend the coverage. And the UAV, also the different height, and with a different receive signal to noise ratio, they will have the different flight differently. And also the radius is cover will be different. So in other words, okay, when you talk, this is another example, when you talk about the UAV, I mean, because it's X, Y, and Z, and then, okay, when you have Z, you have triangle, the distance, you will have the trade-off of the coverage and the performance. So your result will be kind of nonlinear. And so basically this is the case. So there will be optimal point with a different setup, with a different height, okay. And also this is a relay, and where your relay should be located, and a similar thing. And I remember Dr. Wang have done something check for the base station. And for this kind of, I mean, base station, because the antenna, typical antenna is tilted down, because I mean, everybody on the ground, right? We are not Superman, okay? And so all this antenna is tilted down. So even though your UAV is flying next to the base station, very close, but because the antenna is tilted down, so it will not connected well. So in this case, okay, you need to consider kind of the map, the coverage map, not only on the ground, but also on the sky. So it will become much more complicated. And the research, they have the different objective for communication quality, communication with the frequency allocation, power control, and also the location, dimension trajectory. Anyway, so the first case we study is a power and trajectory planning. This is published by JSEC. So you have the flight trajectory and the power control. So basically this is the case. And then you want to, oh, by the way, okay. For this flight trajectory, this energy consumption is typically 10 times than the power control, transmission power control. So, but still, okay, they are comparable. But on the other hand, okay, I saw some paper with this edge computing, and then they try to say, okay, the computer on top, okay, so computation power is 1,000 times smaller than your transmission power. So basically, okay, then it's negligible power. So pay attention to this power level, okay. Flight power is 10 times than the transmission power. Transmission power is much greater than the computation power. Okay, overall, we want to maximize the overall capacity plus many different constraints. Okay, you put all these physics there. And then for algorithm design, it become a non-convex, non-concave problem. And then, okay, typically we typically can divide this problem into two sub-problems. One is for power planning, mine is for the trajectory planning. So this is obviously, okay, the block descendant algorithm. So the so-called block descendant, you consider this as a Yushan, okay, on top. So in the middle, okay, it's a high. You do the maximization. You're starting from any point, try to connect it to it. You go to the east first, and the north, and the east, until you reach to the top. So this X is basically, for example, transmission power. This X2, this X2 is basically trajectory planning. So you can do the iterative until you reach to the point. However, for this block, this is called block descendant problem, BCD solution. For such kind of things, okay, convergence can be very slow. So in order to do that, Tom Law have this B-sum, block successive upper bound. The basic story is starting from this initial point, even though your curve might be non-convex, I add a quadratic upper bound for it. The good thing for quadratic upper bound is that at this point, at the initial point, the value is 0. So the bound value is 0, so it's the same point. And also because the quadratic, the first order differentiation is linear. So at this point, it's still 0. So in this point, the gradient is the same. And the third thing is that because it's quadratic, it's an upper bound greater than equal to 0. And this quadratic will drive the original nonlinear function into a very convex function. So as we know, it's a very convex function, the convergence is very, very good and guaranteed global optimal. So in this case, okay, you're starting from this point, this is already contour, and this is a new contour by adding the upper bound, quadratic upper bound in x1 direction. So instead of going to the black one, they go to the red one. And then in the next round, they add the quadratic over the x2 direction. And then the red one is a new contour compared with the original contour. And then it will go much faster to the destination. So this is a very, very, very kind of fast algorithm. And here we have simulation setup for the different tasks. And here we show that the trajectory planning and the transmit, we take alternative until very quickly converges. Okay, so this is the first example. The second example is my last work on my PhD, my postdoc, okay. And so basically I have a UAV. I'm trying to fly into the network. Those are the kind of either UAV network or the ground users. I want to fly to the location where the overall connectivity is the highest. So how can you quantify the connectivity? This is a graph. You will have Laplace matrix, and on the edge, you have the channel capacity, so you can quantify it. And then the maximum, second largest maximum eigenvalue is called Fidelity value, which is represent the connectivity of this graph. So I want a UAV to fly to the direction such that this kind of eigenvalue becomes larger, so that the network is more connected. So I want the UAV to fly to the position that can connect most of the people together. So this is what the paper is doing. And another paper is with Valisat. It's basically we have some UAVs. The UAV can either do the relay or do the sensing. And how can you group the people together, the UAV together to implement a certain task? And for example, okay, in some courses, you will have the group project, and the 3 people, up to 3 people, 1 to 3 people can work together. Then you will find somebody who is good at organizing, good at programming, and good at writing. And then they form a team so that they can implement the thing. So basically, this is a kind of a coalition game solution. And then, okay, you will have the UAV assisted sensing. So the UAV will try to sense at different places and then try to increase the coverage and then do the sensing area. And for UAV, they will have this kind of sensing the agriculture and the wildfire, Australia, for example, and then all these things together. So here, this is a UAV developed by Beijing University, and they have a camera and we put the air quality sensor to it, and so that they can sense for the different places. And also they can they can go to the important area to reduce to reduce the latency, or they can go to some places like around the stadium. There are so many people using the wireless phone, so the local base station is not good. So the UAV can use as a local base station, flying base station, to increase this kind of EMBB, try to increase the capacity. And also you need to understand the interference. Your interference is not only to your, to your base station, but also, between downlink and uplink kind of interference. So when you try to design this one, try to be careful for this. And there are research challenges for the objective, for sensing communication quality, and also the trajectory planning, communication for power control, and frequency allocation. So for the second example, we talk about the UAV sensing with air quality, and this is a collaboration with Beijing University. And for air pollution, and well, this basically cause a lot of death, and basically it's a kind of air quality index is a value related to PM 2.5, and the higher the worse. And this is the Beijing map. And the problem for Beijing map is that, okay, they only have a fixed location, and it's 2D map. And then how could you know the AQI index around here? And also only 2D and very coarse-grained. So we want to have the fine-grained 3D real-time profiling. So what we do is that, okay, we have the UAV with a sensor, so that we fly for the different places, and then we generate a real-time kind of a solution. And here, okay, the UAV can fly. This is a kind of 3D location. Can round robin fashion to go to all the different location, or the UAV can selectively fly to the location. And here we use a machine learning Gaussian plumb model neural network to select the optimal solution to do that. And also, when we use this model, not only consider neural network part, we also consider a lot of physical meaning part. For example, there are some constraint on the atmosphere, something like that. So in this case, okay, we put them together, it will learn quick. Moreover, this is a ground station map. This is X and Y, this is time T. This is ground station map, which fixed there, but all the time they have it. And this is a kind of UAV one over the different time. The blue one is a UAV one. Over different time, they fly to the different places. And moreover, we have the satellite one. As I said, the LEO satellite, they can only on the sky for 20 minutes, and then they go to the other side of the Earth. So you will have this slice by slice. Moreover, this kind of resolution is very low. So the key question, you have these 3 types of sources, and how can you merge them together to have the higher resolution? So here we use this kind of sparse optimization, try to use the L1 norm, and then try to reconcile the 3D data, and using this convex optimization problem. And this is basically, okay, when you have your phone, you take a selfie, and then, okay, take your selfie, and then try to, you will look better. As a matter of fact, okay, do I look better? I use zoom, and the zoom have this kind of beautify, right? This one. Do I look better? I don't know. Okay. Anyway, this is basically an algorithm they use. Okay. And here they have a data site, which website, and demo. And here I want, and also, if you have such kind of good one, I suggest you, good project, I suggest you to go to the IEEE ComSoc student competition. And I will show you the video, and basically, okay, they won the first prize. So this is a video.
In a recent report
hear the
from the
sound?
World Health Organization,
Can you
air
hear the
pollution
sound?
has become the world's largest environmental health risk, as it's responsible for 1 in 8 of deaths globally. Air pollution is harmful to humans and ecosystem, and monitor the emission of air pollutants is on demand. Air Quality Index is defined to quantify the degree of air pollution. AQI is calculated based on the concentration of a number of air pollutants such as PM2.5. A higher value of AQI indicates that air quality is seriously polluted, resulting in a greater population may experience harmful health effects. AQI monitoring can be completed by sensors at static stations, but there are only limited stations which provide only static two-dimensional AQI map without height profiling. Moreover, they are spatial-temporal coarse-grained. In reality, AQI has intrinsic fine-grained changes in meters, particularly in urban areas. In this project, we design ARMS, a mobile sensing system based on unmanned aerial vehicle, to construct the real-time fine-grained AQI maps. The architecture of ARMS consists of 4 parts. It first performs data sensing and collection, which is based on the monitoring algorithms. Then we do real-time data analysis to construct AQI map and present it by designing dataset and website for visualization. The system includes an UAV and an air quality sensor mounted on the UAV. The sensor is fixed in a plastic box with vent holes. During one measurement, the UAV is programmed with a trajectory. The sensor uses a laser-based AQI detector that can provide high accuracy for common pollutants in AQI calculation. The values of these pollutants are real-time recorded. Intuitively, more measuring samples can introduce an accurate AQI map. However, the UAV suffers from the battery constraint. To solve this issue, we use monitoring algorithms to measure only a few locations and propose a model to estimate AQI value at unmeasured locations, then generate the whole map. The monitoring algorithms have 2 steps. The first step is complete monitoring. We divide the entire space into a set of cubes. In complete monitoring process, ARMS measures all cubes continuously and builds baseline AQI map. The second step is selective monitoring. Based on the baseline map, we then choose to only measure several target cubes to update the real-time AQI map. These target cubes can be obtained by analyzing the map that was built last time and are sufficient to profile the entire AQI map in a given space. The estimation model consists of a linear part using physical model and a non-linear part using neural networks. The model is evaluated to perform high accuracy in estimation. There are many applications for ARMS. First, ARMS can generate real-time AQI maps in typical 2D and 3D scenarios. These fine-grained AQI maps are important and meaningful due to the intuitive reflection of AQI distribution over a certain area. Moreover, by using ARMS, the outdoor AQI maps can give people instructions on whether you need to wear masks or not. In office building scenarios, ARMS can tell whether you need to open windows or an air purifier. The AQI map can also help design the ventilation systems for buildings. We have published our dataset that contains 100 days data for both 2D and 3D scenarios. Also, we designed a website displaying 3D AQI maps of Peking University. The data can also be uploaded by crowdsourcing or sensors. Using ARMS, the fine-grained AQI details can be learned and used in many areas.
Okay, yeah, let's find some other application along this line. And because I work in this, I live in Houston, and there are a lot of oil companies. And for oil company, they want to find this underground kind of infrastructure. So they will have put a lot of sensor here. and then they have a bomb and it generates a wave. And the wave hits a different layer and bounce back, and then they get the data. And the problem for such thing is that, okay, this is a square kilometers. And then the data, typically, okay, they are located in the middle of nowhere. There's no kind of cell phone structure there. And using Wi-Fi ad hoc is take hours or even days to come back. However, okay, to deploy this one costs millions of dollars per day. If they can get the data back quick, and then okay, and then I mean even half hours quicker, and they can save a lot of data, a lot of kind of money. They prepare the source for another bomb only for 20 minutes. So if they can collect the data quicker, they earn a lot of money. So what we do is that we have UAV put a UCLU, this is a millimeter wave, and then fly on top of this kind of sensor network, where the trajectory planning and such that they can collect the data. And sensor, they can select to wait for the UAV or use a multi-hop to send it back. So this is joint consideration. Okay, it will be a very interesting topic. And another one is a server, and basically using UAV to see this like a buffalo grass. The buffalo grass is highly related to the oil kind of pollution, and then if they can use a machine learning to find the buffalo grass. So when they do the survey, instead of fixed truss, they can use the machine learning to see the buffalo grass and then train the UAV to find the places. And so basically this is a project, what we do. Okay, so this is about UAV. And next we talk about HAP. And for HAP, if it's below 16, it can directly communicate. And if it's above 16, then you need the terminal, as I mentioned. And then, excuse me, okay, don't worry, it's not COVID-19, okay? Anyway, and so we have this service ambiguity. So basically, okay, the user can directly connect to the HAP. This is a standalone system. Or you can have this kind of hierarchical. So below you have this kind of base station cover, cell phone network, or you can cover. So this become a hierarchical structure. Or you can integrate together with the satellite, and multiple kind of HAP can connect it to each other. And that is a very kind of interesting. For example, I used to work with Tencent, and for them, they need the edge computing, and then typically they put on the base, put into this kind of around the base station. And however, sometimes they need to cover a larger area, and sometimes dynamic. So what they can do is that they can put this kind of resources over this kind of HAP, and then kind of move around and dynamically allocate the resources. So this is the case. And for the beam, this HAP will point it down for the beam, and this is from David Gray's equation, the paper from David Gray, and this is a theta, it's the angle, and then basically this diversity gain you can get. And also, okay, the HAP will move, so this is a moving distance for this one, and also vertically they will also move. So what is the effect with the new beam? So because it's still within the atmosphere, and this is the case. And also sometimes HAP is a kind of inclining motion. So in this case, okay, your beam also kind of shaking around. So in this case, okay, what is the effect for that? So this is basically okay, beam forming kind of consideration, and the major kind of, I should put the citation here, and David Grace from UK is working on this area. And for research challenge, it's coverage and capacity extension. So we have the access control, terrestrial HAP, and etc. for interference management. And also, okay, we have the beamforming for the interbeam interference and intercell interference. So how could we optimize it? And also topology management. We have the energy traffic aware dynamic topology management. We can switch on and off, and also okay, handover between the HAP. So let's talk about the example. This is a joint HAP access and LEO satellite by call in 16 machine game approach. And the motivation is that the traditional, terrestrial network with limited backhaul capacity cannot guarantee this coverage, and traditional satellite, will have delay, and HAP provided the trade-off, and then we try to integrate the HAP into the satellite for this one. So the goal is that, okay, we have this IoT, the air-based access for the remote area user is a key issue to the space ground network. And we have IoT on the ground or the mobile in the remote area without access. On the top, we have the HAP, and on the satellite, we have the global coverage. So the key question is that, okay, how could we minimize the total revenue of the site, maximize the total revenue, and under many different constraints. And so basically, which one you should link to, map to, and below which one you should map to. So this is very interesting. And then, okay, first the mapping itself is kind of NP hard, and then we try to use this kind of matching algorithm, try to kind of try to kind of map in a quick way. Here we use this kind of, because we have three different partners. Here you also have 3 satellite, HAP, and user. So we use a man, dog, and a woman preference list. So the man is a satellite, and the woman is a user, dog is a HAP. So this is a famous algorithm called man prefer woman and a woman prefer dog matching algorithm. So in this case, we can solve such kind of problem into a kind of a suboptimal solution. And on the other hand, okay, after this one, your kind of user will change. Well, your satellite is moving, and but how this kind of user change, you don't know. But how the satellite is changing, you know. So in this case, how could you handle this dynamic? So basically, okay, we use a random path to pairwise stable matching between this one. So by doing this one, we don't need to calculate this algorithm for each time slot, and we can update it quicker. Okay, so basically this is the key idea. And here the performance optimal solution, or proposed suboptimal but the linear complexity, and the other existing solution in the literature. Okay, and then the next we talk about the satellite network, and so again, okay, as I mentioned, okay, for SpaceX, you cannot use this kind of phone to directly connect it. You have to have a base station. Well, for the satellite phone, you can directly connect it. And then you have the spatial diversity. So basically, okay, you can connect it to the multiple satellites. For example, for GPS, you only need to connect it three GPS, or 3 satellite GPS satellites to know your XY location, and 4 to know your XYZ location. But if you have more satellites, then you will have better diversity. And also, if the LEO is not working, you can go to the MEO or GEO. And for example, for Chinese kind of location, it's a mix of the LEO, GEO, and the MEO. The reason for that is that, okay, the GPS is a LEO system. It's so easy to get attacked. But for MEO and GEO, there's basically no way to get attacked because it's too far away. So in this case, you have this kind of diversity, spatial diversity. And also you need the seamless coverage. Currently, okay, this kind of SpaceX one, and this Elon Musk one, they need to put dozens of thousands of there. Currently, they cannot have seamless coverage yet. They need to send more satellites there. And they want to have higher capacity. And a few days ago, they say SpaceX and Starlink can have 60 meg. Yeah. It surprised me, okay. Because I used to work for a huge network 1998. And at that time, they are claiming 2.5G. Anyway, so yeah, maybe I'm wrong. Okay, successful transmission. You want this angle separation. For example, there are two satellites in the same angle. Then you don't want to have this one shoot to kill two birds, right? Anyway, so you don't want to communicate in this way. And also delay tolerant. You have to have a low orbit one. I mean, Geo and Leo have a too much kind of delay. And then you have the research challenge, improve the spectrum efficiency, and provide the coverage and integrate with a terrestrial network. Integration is very interesting, and also deployment of LEO satellite constellation. Okay, so we have another example of satellite communication, collaborate data scheduling with joint forward and backward induction in small satellite network. So the basic story is that, okay, my satellite will moving with a kind of a deterministic one. So basically, okay, so where my satellite is located, I can, at a certain time, I can calculate it. On the other hand, okay, for this mission arrival is a kind of, uncertainty. So here we will use this kind of Markov mission arrival model to quantify. And then the key question is that, okay, suppose on the ground, we have this kind of sensors which follow these distributions. And then for satellite, it's moving. And not like UAV. UAV, you can control the location where to go. Satellite at a certain time is just be there. This is deterministic. And then the key question that, okay, when should I do the transmission? When should I do what? Data forward, such that I can do the, I can try to do this kind of optimize. So in this case, okay, typically if you have Markov one, you will have this kind of forward, this trellis one, and look like Viterbi decoding. And then we have this different state, something like that. This looks like a trellis formulation. And here the problem is, the difference is that, okay, compare with if your satellite is auto random, then classic Bellman equation can be done. But your satellite is fixed. If it's a fixed, I know the next time what you'll do. Then what I can do is I'm doing the backward induction, and then I can get an optimal solution. However, my arrival is a random thing. I'm supposed to do the forward Bellman equation. Then there's a conflict for that. And then what we can do? Well, what we can do is that, okay, we propose this forward and a backward kind of induction. So the problem formulation is that, okay, the overall is my immediate payoff plus the future payoff. And this is Bellman equation. But, okay, if I do the expectation, I mean, for the arrival rate, I can do the expectation. But for the service rate, it's a deterministic. I'm supposed to do the backward induction. So in this case, what you do? So we propose a joint forward and a backward induction algorithm, and then we show that, okay, it's very near optimal, and compare with the other algorithm, it's a kind of improvement. And this is a kind of one step ahead based on the unique structure of the satellite, such that the traditional Viterbi algorithm cannot kind of fit. Then we have to go one step ahead so that, okay, we can have this solution. So you can see that, okay, this is I like this paper a lot in the sense that, okay, it is not just take an algorithm to a kind of scenario and then do the result. Instead, in this scenario, there is some kind of unique things that you have to consider. That, I mean, the traditional algorithm cannot kind of fully take advantage of this unique characteristic of this scenario. And in this case, in this paper, in this algorithm, we consider of this one, upgrade the traditional algorithm, and then work specifically for this satellite scenario. And so that's the reason, okay, it's very nice. I like it very much. And finally, let's talk about this integration of aerial access network with terrestrial network. So this is the AAN, and you have all this different structure. And the technical enabler is a software-defined network. We define the network architecture for centralized control, multi-coupling data plane and control plane, suitable for multi-layer network. This is look like a network virtualization, right? Network virtualization, you need this kind of software-defined network. And then the application to AAN, your challenge is not trivial to coordinate ultra-dense multi-layer AAN. And so basically it can be the reason is that, okay, your ultra-dense LEO satellite for SpaceX is 60 kilo. How much signal processing capability you can put there? Okay, so this is one example. And the solution is that a set of small LEO satellite, HAP as a controller, and so basically they are kind of grouped, like work together and coordinate together, well organized for data processing and routing. Okay. And also the college radio, another type is group of unlicensed users try to share with them to tackle the spectrum problem. And then we have the challenge, no dedicated spectrum, and the solution is a second user, and the example is UAV and HAP. So basically, they can use this kind of college radio technique. And caching schemes to store the caching, and the challenge is where to cache. Serve more user or faster access. The solution is to integrate different layer. And so basically for different layer, they may cache for the different content so that, okay, they can maximize this caching content. And for example, okay, now, okay, even Trump is kind of ban TikTok. But TikTok, okay, this kind of caching, how much video is it? So you need a very careful caching. Otherwise, okay, the network is kind of get a lot of burden. So the caching, okay, the caching for this kind of a video website like TikTok is a very, very kind of hard research for this. Okay. And when we talk about the satellite area integrated computing in disaster area, I mean, user association and offloading decision. The disaster might lead to collapse of traditional terrestrial infrastructure, UAV at the aerial base station for IoT user to perform the sensing task. However, limited payload and short time of UAV is a challenge. So basically, we want to have the LEO satellite and HAP together. So the LEO satellite and with MEC server operating in Ka-band connected to the gateway, to the terrestrial gateway, and HAP and with MEC server and almost quasi-static at fixed altitude. Satellite will move around. And they have two types of users and limited computation ability. So basically, this is the overall structure. And then we have the front haul link from the two-tier user to the HAP operating in Ka-band, and this kind of user with a different user with a different channel. Okay, and the backhaul is from the HAP to the backhaul link is from the HAP to LEO satellite, and then they have the computation locally is actually with the HAP or offloading to the LEO satellite to the other places. And then we have the computation rate and the communication rate, decision variable, something like that. And overall, we want to maximize the sum rate of the system by optimizing the two-tier user association offloading decision with many different constraints. And this one can be formulated as a hypergraph matching algorithm, which is NP-hard. And I have a slide on my website and which talk about hypergraph, and you can check to see how this kind of algorithm is done. It's an extension of the matching, and we talked before. And finally, we talk about AAN 3GPP, and this is the current update for this kind of investigation. So they are still trying to standardize it, and this is a kind of information you can follow up And the potential degradation with a, you can combine this AAN with a different NOMA, edge computing, and you can do the signal processing like beam alignment, network coding, secure transmission, or you can have the network optimization like the routing and spectrum allocation. So here is some kind of publication and related. And we have one book published, the other is in preparation. So finally, okay, advertisement on my group, and feel free to visit us or join us. And except for, I mean, besides for study, we do everything else, okay. And I hope that, okay, I mean, the COVID-19 is over, will be over soon. And so that we can restart our activity. And this is a good side. And the bad side is that, okay, and for our group, if you meet deadlines, okay. If you're not, you are missing the deadline, the penalty is a half marathon. I'm just joking, okay. Okay, thank you very much. Any question? Anybody have a question?
Thank you, Professor Han.
Okay, thank you.
Yeah, I have a question.
Sure.
Yeah. So from your opinion, I think